Last section of chapter 6 is exponential growth and decay. So we're going to find equations of populations that obey the law of uninhibited growth. So that's if there's nothing that limits the amount of growth. There's unlimited food, say, and space. And then we're going to find equations of populations that obey the law of decay. We're going to skip Newton's law of cooling. If you need that in the future, you'll pick it right up. And I wanted to talk about logistic models because I think they're more interesting and useful. So first we're going to find equations of populations that obey the law of uninhibited growth. So there's many things that obey that law of exponential change. Things like continuously compounded interest, if you have a bacterial colony that has unlimited amount of space and food, insect populations, and then we also have radioactive decay, which is exponential decrease. So this law is exponential. It looks like A of t, so you're saying capital A of t, it's a function of time, equals capital A sub 0 e to the k t. So the k times t is in the exponent. A sub 0 is the beginning amount. And k is called the exponential growth factor, wherein k is bigger than 0, or it's the exponential decay factor if the k is negative, and t is time. And remember that everything has to match up. So if your decay factor or growth factor is in days, your t needs to be in days. And if your growth factor or decay factor is in years, then your t needs to be in years. So everything needs to match up. So let's look harder at the growth in the number of bacteria in a colony over a time. And so according to our general formula, we'll have A of t equals A sub 0 e to the kt. And remember that A sub 0 can also be written as A of 0, but that's more writing. So it's just kind of a convention that everybody says, let's write A subscript 0 to represent that because it's less writing. So A is representing the number of cells in the bacterial colony at any particular time. So let's use a more representative letter of n, the number of cells. So then the formula looks like n of t is n sub 0 e to the kt. Okay, A is just amount, so it's very general. So let's be more specific with this example. So for our example, we're going to begin with this formula. It's given in the problem. It says n of t equals 1000 e to the 0.01 t. So the number of bacteria in a colony in hours obeys this law of uninhibited growth. So let's figure out what's the number of bacteria at t equals 0. So I want you to use proper notation. Say n of 0 equals 1000 e to the 0.01 times 0. Well, e to the 0 power is 1. So this equals 1000. And when it's a word problem, there's usually units that need to be included in the answer. So you need to write 1000 bacteria. Okay, so then B, say what is the growth rate of the bacteria? Well, it's 0.01, but it's times time, so it's in hours to the -1, which is a very weird sort of unit, but it does need units on it so that when you multiply by hours, you get something that doesn't have units. So this could be per hour, and in fact it's 1% per hour, because remember the decimal 0.01 is the same number as 1%. So the population growth rate is 1% per hour. Okay, so then if we want to know the population after 4 hours, we're going to say, what is n of 4? So it's going to be 1000 e to the 0.01 times 4. And let me get my calculator out really quick so I can find out about how big that is. So we multiply the 0.01 times the 4. Then we're going to do e to that power multiply it by 1,000, and I'm getting about 1,041 bacteria. Although it could be argued that 1,040 would be the correct answer, but they're bacteria, so you can't have the 0.8 of a bacteria. That wouldn't make any sense. And so you actually would probably, if you counted them, you'd have 1,040 because that 0.8 of a one wouldn't have actually appeared yet. So you could argue that either way. So then the D part says when. So as soon as it says when, what are we solving for? T. When will the number of bacteria reach 1,700? Well, N of T then is going to be the 1,700, and that equals 1,000 e to the 0.01 T. So remember that we need to isolate the exponential. So I'm going to have 17 over 10 equals e to the 0.01 T. So then I have the exponential isolated, then I take the logarithms of both sides. Then the property of logarithms, it says the exponent can come down in the front and multiply the ln of e. But remember that the ln of e equals 1. If you take the log of the base, you always get 1. So I have that the ln of 17/10 equals 0.01 t. So I'm going to divide both sides by 0.01, which is a very strange looking number. So I'm going to want a decimal approximation, because that's what will be useful in this problem. And it looks like about 53 hours. If you don't have anything that says how to round, just use your best judgment. So after about 53 hours, you'd have 1,700 bacteria. And then if it says, when will the number of bacteria double? Well, that's asking of if I started with 1,000, when will I have 2,000? So this is the E part. So see that when we both divide both sides by 1,000, you get 2. So 2 equals e to the 0.01 t, then the ln of 2 equals the ln of e to the 0.01 t, which we just found out earlier is 0.01 t. So t equals the ln of 2 over 0.01. So how long does it take until the bacteria double? I'm getting about 69 hours. 69.3 if we want to round to nearest tenth. So it takes about 69.3 hours for the number of bacteria to double. So this has actually a special name. It's called doubling time. And it's a way of doing a quick analysis of an investment. If you say, what's the doubling time? And you look at two different investments and see what the doubling time is. You want the faster one, right? Okay. So number 5 is a different sort of a problem where you have to figure out more of the bits and pieces of it. So this one I'm going to get you started and give you some parts, but then I want you to do this one in class together. So this just says it obeys the law of uninhibited growth. So we're going to write the general equation for the law of uninhibited growth. Express n as a function of t. So this is the part A. So then B says if there are 1,000 mosquitoes initially. So now I know that n of t is 1,000 e to the kt. So I've used that piece of information. And there are 1,800 after 1 day. So that says when t equals 1 day, what is n? It's 1,800. So 1,800 equals 1,000 e to the k times 1. Well, the only thing you don't know here is the k. So I'm going to let you figure out how to solve for the k. And then I want you to write the formula that you get. Fill in your k here. And don't round it off, because exponential functions are very touchy. They're very sensitive to small changes in input. So if you round it off too much, it could throw your answer way off, like noticeably off. Okay, so you're going to find the k, and then it says what is the size after 3 days. So you're going to find the n of 3. And then I'll let you figure out the c part together. Okay, so then objective 3 is law of decay. So let me make a separate movie for that because it's kind of a different topic.